Okay. Um, Good evening, everyone. Welcome to the week 12 problem solving session. So, this is the last problem solving session. And so, my name is Bhavya. I'm a PhD scholar at IITM. Okay. And again, before I start, I announced this last week too, but I want to announce it once again that tomorrow, that is Wednesday, tomorrow, today's 13th, I guess, 15th, 16th. So, okay. For tomorrow is 16th April. Okay, tomorrow 16th April, um, we'll be having an extra discussion session. Okay, we'll be having an extra discussion session where we'll be talking about all the different various topics within the course, and you can tell me if you have any problems understanding a certain concept. Then we will discuss that particular concept, and if it is out of your own interest that you are pursuing something which is related to the course, then I'm happy to discuss that too, and or maybe assignment problems and so on. And because I think the exam date is also nearing, and so maybe it will help in that too. And so tomorrow, by the way, Wednesday, 6 p.m. to 8 p.m. The usual timing, but except it's Wednesday. Okay. So having said that, I think we can begin. And today, I won't be doing much. This might be a much more shorter session. Okay. Um, because firstly, this week's topic is parameterized algorithm. Para Okay, and this is a huge area of research in its own right. And so, what I want to say is that uh, the area is itself a large budding area with a lot of research right now, and it may be a bit non-trivial, and to come up with the techniques that they use, it may not be very easy, and so I do not imagine that you will be expected to solve questions that are from problems that are not taught to you. Okay, so that is one reason, and that I'm not going to cover it too much in detail. But anyhow, I'll tell you the concept of parameterized algorithm, and I'll give you some examples about it. Okay, so having said that, let's begin. Okay. Okay. So what is parameterized algorithm? Okay. What we have is, so I want to begin directly with an example. Okay. Um, Let me talk about something that one of you pointed out. I think um, it was Goel or Kishore, someone that pointed out about, and so for example, take these pseudo polynomial algorithms. Okay. Pseudo polynomial algorithms. And what are pseudo polynomial algorithms? Well, these are algorithms that appear to be running in polynomial time, okay, but actually they are not. An example is, you remember the Ford Fulkerson algorithm? Okay, you remember the Ford Fulkerson algorithm? Well, if you don't know, it's the algorithm itself is not important right now. What is the problem? The problem is maximum flow. That is, if you are given a network of nodes with a designated start and end vertex, and each of these edges are labeled with a certain capacity value. Okay, let's say 10, 9, 8, 10, 6, 5, 2, 1, and so on. And you want to compute the maximum flow that I can send through this network. Okay, and it had, if you remember, it had its capacity constraints, flow constraint, and so on. Now, what is the maximum flow that we can push through this network from the source to the target? Okay, that is the max flow. And there were better algorithms in fault Fulkerson, but if you remember, okay, recall that the time complexity of Ford Fulkerson was f star times the number. One moment, I should reduce the brightness. F star times the size of f star times the number of edges, something like that, if you remember. Now, what is f star? F star is actually the maximum flow within the network itself. Okay, and this looks polynomial. Okay, it looks polynomial, but it is actually not polynomial. And it appears polynomial, but it is not actually polynomial. Why? And then we had a long discussion regarding it. Since f star is represented in binary, okay, and oh, sorry, what am I saying? Since f star is the natural number here, okay, and it could be as large as exponential, okay, because the input size is polynomial in terms of binary bits, and f star could actually be as large as exponential, okay, and this is the time complexity of go ahead.
So I have a query here that so many times we used to say that input in terms of this thing. So can you write that thing here that input in terms of the bits or input in terms of what, so that this would be an indication that now this is going to be a pseudo polynomial kind.
Okay. So see, this particular f star, right, is not okay. I'll remove, first of all, I'll remove these lines here. Okay, so f star is max flow, okay, through the network. Now, f star is the max flow in the network, okay, and let's do some analysis. You want to actually visualize that why it is exponential. That's what you are sort of saying, right? Well, by talking in terms of input.
It's not only the visualization, but then you often used to make one statement that the input is in terms of the number of the bits, kind of a thing. Often you used to. So can you
we should compare it with the size of the input. That's what I was saying before, right? And with respect to the size of the input, if it can go exponential, then it is pseudo polynomial. I mean, that's what I used to say. That's right.
Okay.
So just to demonstrate it once, f star is the max flow in the network, and here f star is not a string. Okay, at least it's not a. It is not the size of f star. That is not the binary. When we represent f star as binary, that's not what I'm talking about. F star is an actual number. It is a numerical factor. Okay, for example, if I have this network, for example, here, consider this network itself. Okay, let's say this network has max flow as 17. Okay, so f star equals 17. I'm not talking about the binary representation at all. Okay, now so this is what I'm talking about. But to further talk about it, what I mean is, so if I have a network and it has these own set of weights, right, on the edges, which represent the capacities, okay, and I have the source and target. So what I can say is, okay, it may always be that, okay, so it may always be that, let's say this is W1, this is W2, okay, it may always be, and what is the input? Input is like, I have the graph, okay, and I have the weights of the graph. I have S, I have T, and I have the weights of the graph, W1, W2, and so on, till W, the number of edges, right? W3, W4, and so on, and so on. I have this is the input. But how is the input given to me? It is given to me in binary, right? So this,
So where is the input in binary here?
yeah.
So where is the input in the binary here?
So what I mean is, like, this is given as an adjacency matrix. Let's say it's given in binary. Okay, for example, this is the size is v square, and this is given in binary, so it will be represented in log the total number of vertices, and this is also taking how much space, log number of vertices, to represent in binary. Similarly, these weights are given to us in binary. So if let's say W1 was supposed to be uh, let's say 32, okay, then what is the binary representation of W1, which is given in the input, is what? It's 1 0 0 0 0, right? Oh, or rather one more zero, I think. No, I think it's correct. 1 0 0 0 0. This is the binary representation of 32. That is how it's given to us. Is that clear?
Okay.
Okay.
Yes.
Okay. So this is given to us in, and okay, 32 is, you may see, like, it appears. Oh no, that's totally fine. 32 is represented with how many bits? Log of W1 bits. For example, log of 32 is 5. So it is represented with 5 bits.
Okay. And so why did you write this S as log of V? It is understandable that S would be represented by the log of V. But then while writing this as log of V, you are assuming that V is the input.
Yeah, I mean, how many bits do I require? These are all bits. Sorry, log of V bits. V square many bits.
So if V square many bits are required, then what this V square will represent? So does this mean that this V is given as the input? I mean, is this something which is known to us, and this is something which is a polynomial kind of a thing?
Okay. Let's say it is given in the input. Let's say I give, like, in the beginning I give V many ones followed by a 0, and then I give this input. Okay, we can always do something like that. Okay, the encoding is always that I give V many ones and then followed by a 0, then the remaining information. So I can always, my algorithm can always count the number of ones in the beginning and then say, oh, there are V many vertices, and then accordingly start, partitioning this into, okay, this is the adjacency matrix of the graph, and then the next log V bits is the S, and the next log V is the T, and so on. Okay.
So then, I mean, what is given as an input here? So apart from the V, so can we assume that the mod of E is also given as an input, and it is known to us? I mean, how many values can we consider as an input here?
No, okay. See, as long as the input, no, that's totally fine. I mean, because see, V is smaller than V square, no? So V square is already a dominating term in terms of asymptotics. You get it, right? This is already a dominating term in terms of asymptotics.
Yes.
So it's not a problem. I can include size of E, size of V, anything, but order V square is already representing all those things. So it does not blow up too much in size if I if I put represent V, then E, and so on. That's not something that is causing a problem here. Okay. What I want to actually represent is, why is this F star causing a problem? Okay. And that's because if I have W1, W2 as all the weights and so on, and then this takes how much? Log of W, the Eth edge, the last edge, and number of bits. Okay. Now what I can always do is I can replace these with all of them by log of wi bits, where wi is the max capacity, max possible capacity. Take look at all the edges, okay, whichever is the max capacity, that is how many bits I'll allocate. And because all the weights are either less than or equal to that particular max capacity, okay, all the weights are less than that max capacity, let's say it is 24, then I just need log 24 bits to actually represent everything. For log 20 bits for each capacity for every edge, because 24 is the maximum capacity. Okay, that is clear, right? Now, yeah. Now, but see that, note the following. Okay, the max flow, okay, which is also f star, is at most, okay, max flow f star is at most the sum of all the weights, right? Okay, max flow is at most the sum of all weights.
Yes.
Right, because I cannot push more than that amount. Okay, and sum of all weights, and this is something. Okay, so the number of the f star. Okay, now the okay, this is like this now. And if so, what does it mean? It means that, and but what I'm saying is, it is that, but let me do a weak asymptotic. Okay, let me show a weak asymptotic max flow. Okay, there could be a case. This is the worst case. Okay, this is the worst case. Worst case is when max flow is equal to W1 plus W2 plus W3. Nothing is stopping us from this happening. I can always build a graph that will maybe sum up. It could be a trivial graph like this, S T, for example, this graph, right? It will be the sum of all the weights. Okay. Nothing is stopping us from the worst case happening, or it is very close to the worst case, even if this is not possible. Okay, it is the sum of everything. Now, f star, okay, is, this would mean that f star is at least, okay, the wi, where wi is max capacity. Right, the f star is at least wi, where wi is max capacity, because if the sum is already equal to f star, then of course f star, I'm just picking one candidate from this, which is maximum, and then I'm taking this, I'm putting it here. Then of course f is at least the wi, one of these capacities, which is maximum. Okay, in the worst case, we are only talking about the worst case scenarios. Okay, now we have this, but what do we know by property of log? Okay, like I have mentioned before, wi is equal to 2 to the log wi. Right, is that clear? wi is equal to 2 to the log wi. Okay, so this implies that f star is at least 2 to the log wi in the worst case. Okay, but log wi is a factor in the input. It's one of the inputs. It is a part of an input. You get it?
So, but in this entire discussion, I mean, boils down to that, I mean, whatever quantity we are getting in the time complexity, in the execution time. So this quantity may become so very enormously large that this becomes exponential of the other term.
Exactly. Exactly. It could be very large, because now what I'm saying is f star is 2 to the some input, one part of the input. Okay, and we are saying the total length of the total running time of the algorithm f star times e. So running time, which is equal to order f star times e, is equal to order 2 to the log wi times e, or it is equivalent to this. Not it need not be exactly, but so that is represented by, because there is at least here that is represented by theta, right? So uh, something like this on average you can expect. This may not be always, but in the worst case this could always happen. Okay.
So, but then this supports the argument you made for the knapsack problem. If you remember, for the knapsack problem, I said that the complexity is of the order of n into w. And then I said that it may so happen that w becomes so very enormously large, like
Right. So the knapsack, yeah.
So in the case of the knapsack problem, the complexity was of the order of n into w.
Right.
And n is the number of the articles, isn't it? N is the number of the objects.
Number of objects, that's right.
So if I take the value of n is equal to 5, then I said that it may so happen that the total weight may become greater than or equals to say 32.
That's right.
So therefore, I mean the complexity of the algorithm is not polynomial, but it is pseudo polynomial.
That's right,
And
exactly.
more or less the same thing is happening here also in the case of the fold percussion, that quite possible that this f star somehow may become say the sub say so quite possible that okay, so this f star may becomes exponential of the w kind of thing.
That's right.
So now my query is that is this common for all the algorithms that are being solved I mean in the pseudo polynomial time, that we would be getting the execution time in terms of, I mean, one parameter will appear in the execution time.
Exactly. No, you need right. No, see, you need to compare it with the input. Okay, it is not true for that for any algorithm that you can achieve this. Okay, just give me something that can be solved in P. For example, okay, just give me a minute. I need to plug in my laptop.
Am I clearly audible to you? Or do I need to speak a bit louder?
Oh yeah, no, I can hear you, but there is a slight disturbance that I can. I need to make an effort a bit to hear you clearly. There is slight disturbance in. I'm not sure. Is it on your side or my side?
No, I have tried multiple possibilities, but that is the result.
Oh, no, it's okay. Oh, it's okay. It's okay. Okay. Anyway, so no, going to answer your question, this is not like always possible. Okay. For example, give me any polynomial time algorithm. For example,
quicksort, and the complexities of order of L.
Quicksort, yeah, okay. Quicksort has the complexity as okay. Quicksort has it is a bit debatable because quicksort has something like n log n and order n square, but it can have order n square in the worst case, no?
So I would like to take
take something like merge sort.
I would like to take n log n here because then this will include both the term n as well as log n.
So let's take merge sort instead. Is that fine? Because it takes n log n time.
Yes.
Okay, sure. Now, how do you write it in terms of pseudo polynomial?
So no, because this is polynomial.
This is already polynomial. That's right.
So my argument will not fit here. I mean, neither n is so argument won't fit here. My argument will fit only for those algorithms which can be solved in the pseudo polynomial time. And then in that execution time, there would be a parameter, there would be something, a parameter similar to the capital W, and which may become enormously large sometime. So therefore, in general, even though it appears that it is solvable in the polynomial time, but in reality, it is taking its time.
Exactly. Now, but my point is now the following. Okay. Let's say, for example, let's say I let's say in terms of the max flow problem, suppose in the max flow problem the weights W1 to W2 and so on, WE, are always constant. Let's say they are guaranteed to be constant. Let's say constant. That is, they do not change with respect to the input. Okay. Then what happens? I just pick the biggest constant and put it in the Ford-Fulkerson algorithm. Okay, let's say C is greater than all, constant C is greater than all the Wi for all Wi. Okay, for all I. Then Ford-Fulkerson will take some constant times number of H's time. Right. Now it becomes polynomial. Okay, if I have a guarantee that all the weights are very small constant. Let's say I push it a bit further. Okay, let's say I push it a bit further and say that let's say suppose that order. So let's say that now suppose all weights, actually it should be called capacities, no? As we have seen in the course, capacities W1 to Wn can be at most log the number of vertices. Okay, or log the size of the graph, whatever. So we are pushing, log is slightly more than constant, but it's not polynomial yet. Okay, if I do this, so that is W1 to Wn is the value, okay, not the binary representation, is log V. Now what do you have? We have this f star is at least 2 to the log V, in worst case f star is at least 2 to the log V, not log V, sorry, log Wi, where Wi is the max one, but log Wi is at itself at most log V. So f star is at least 2 to the log V. And since 2 to the log something is equal to that something, this is equal to log V, the number of vertices. Okay, but shouldn't it be polynomial one? There seems to be a, oh no, this is correct. This is correct. So now you have the time complexity equals order log number of vertices times E. Now it's polynomial. From exponential, we made it polynomial by simply saying that all the capacities cannot be very large. You get it, right? Now, but the problem is that, if I say it can be polynomial size now, okay, Wi can be polynomial size, that is when it could create a problem. That is when this entire thing may blow up. So conclusion is, this f star can be thought of as a parameter. So if it so happens that the maximum flow, if it so happens that the capacities of the network is cannot be too large, then the maximum flow also, because we already saw, cannot be too large because the capacities are itself small, then my algorithm suddenly runs in a faster time. And I can change this. Now, that is what is meant by a parameter, right? A parameter means some placeholder value which I can actually modify. I can make it less or more according to my need. And can be thought of as a parameter for certain values of the parameter my algorithm runs in polynomial type. Similarly, okay, I'll take Goel's example that knapsack, the running time of knapsack is order nw, where n is the number of items and w is the weight. Now this weight is not, again, I'm telling you, w is not the size, the binary representation size of the weight. Okay, it's the actual weight itself. It's a numerical factor. Whereas in the input, the size is given as log w, is the input binary length. Okay, with respect to that, with respect to log w, w is exponential. With respect to log w, w is exponential. Okay. Now, what I can do is, suppose the size of the knapsack itself is log n, order log n, is logarithmic. Then order nw is equal to order n times 2 to the log w, okay, because w is equal to 2 to the log w. And what did we say log w is? What did we say? W is log n. Okay, we can actually do better. W itself is n. Okay, suppose even if w is n, okay, even if w is n, this can still be 2 to the log w and order n 2 to the log n, which is equal to order n square, if w is n. But remember, log w is capable actually of representing more than n. Okay, log w is capable of representing 2 to the w. Okay, log n in other, 2 to the w. Oh, sorry, w is able to represent 2 to the w. Okay, which is the length of the input. So what I mean to say is, if I modify this w parameter, okay, to be not very large, okay, compared to the input, then my running time can actually be made more or less according to my need. This is, yeah.
So if you write w as log of n, so that is acceptable.
That is still acceptable, but now what I'm doing is I'm reducing the capacity of the knapsack further, right?
Yeah, but then if you write w itself is of the order of n, so then
okay. See, you might say something like w is already polynomial in terms of n, but
yes,
right, but actually w can be very large, because say w could be possibility is w is 2 to the n. This is possible. Why? Because the length of w is n in terms of binary. When I represent w in binary, its length could be n. So in terms of the input length, I'm still polynomial with respect to n, but this binary number can represent a very large number. This binary length, the n length number can represent up till 2 to the n. Agreed, right? For example, if the length is 5, if I set these all to be 1s, I can represent 31, which is 2 to the 5, 2 to the 5 minus 1. Oh, actually not 31, it's even larger. It is 63. You get it, right? So this is your n, this is your w.
Actually, the things were working pretty smooth for the previous example, wherein you said that the weight is of the order of the log of the vertices. It makes sense that if the weight of every edge say cannot cross a very small quantity, then clearly the sum of the weights cannot be exponential.
That's right. That's right.
Yeah. So, but then now in this case, something strange is happening. That now we say that this total weight W. So this W is the total weight. In fact, this is not the weight of
That's right. That's the
individual
size of the bag.
total weight. So once you fix this thing, the total weight is of the order of n. So clearly, this is not the case of the pseudo polynomial, because
This is not pseudo polynomial. I mean,
yes,
right?
because argument is required beyond this point, because the argument relies on the fact that this W may become exponential of n.
Yeah,
And
of course. That is what I was talking about. It could be exponential, but I'm restricting it.
Yes, so once you restrict the value of the capital W, then clearly the graph is going to be solved. Yes.
Right. So, see, so far we didn't do some ingenious algorithm design. Okay. So far we've only changed the parameters here and there, make n less, I mean W more, make the change the maximum flow, change the the size, the weight, and so on. And you might see that it's obvious that it changes. Now, but what I'm talking about is the importance of the concept of parameterization. Okay, I might come into cases where I do not need, let's say, a large W. Okay, I might run into cases where I do not, my knapsack mean is not very large. In that case, this algorithm runs very efficiently. I might only be interested in flows where the only those networks where actually the maximum flow is small. I mean, for whatever reason, let's say all the capacities are small, very small compared to the size of the network. Let's say the capacities cannot be very large compared to the size of the network. Then I can efficiently solve that process. Now, that is the philosophy behind the process of parameterization. Okay, I pick just one parameter, and if that parameter can be accordingly modified so that the entire algorithm can be made to run in polynomial time. That is the concept of parameterization. Okay, so parameterization. Okay, parameterization, or rather, I'll define what are the fixed polynomial tractable. Okay, these are called FPTs algorithms. Okay, fixed polynomial tractable algorithms, or a fixed polynomial tractable problem. Okay, an algorithm is said to be.
Yes, is this fixed polynomial or is this fixed point? I guess this is fixed point. Fixed point tractable.
No, it's fixed polynomial, right? Okay, I'll just one moment.
Fixed parameterized, I think.
Oh, sorry, yeah. What am I saying? Fixed parameterized. Tractable already means polynomial. Parameterized. Fixed parameterized tractable. Okay. Algorithm is said to be fixed parameterized tractable, and by parameterized you know that the algorithm is parameterized, of course. Tractable represents that it runs in polynomial time. Okay, the algorithm is said to be FPT if it runs in some k. It can be made to run in some k order k times. Okay, but k should be a part of the input. Okay, let's say FPT if it. Okay, I'll just write it all together. If it runs in order k order, not just k, some poly k times n to the order 1 which means constant, for an input, okay, xk, where size of x equals, okay. So this is what you mean by FPT algorithms. And FPT algorithms, in other words, if I have, let's say, give me a problem, for example, vertex cover. Okay, vertex cover. What is vertex cover? Well, the input is a G and a K. Okay, and what is the output? Output is yes if there is a vertex cover of G, vertex cover S of G, such that the size of the vertex cover is at most, should it be at most, at least, no, it should be at most, is at most K, okay, no otherwise. We've already talked a lot about vertex cover. What is vertex cover? It is just a set of vertices where um, every edge is incident upon. I mean, every edge is covered in, rather. Okay. So we've already talked about vertex cover, and so if I say there is, an FPT algorithm for vertex cover, okay, with input GK and time uh, running time order of size number of vertices times this, I'm not putting an exact bound, okay, times something like K, okay, something like K. I'm not giving the exact bound right now. It could be K square or something like that. It just means that if I'm okay with finding not too large of a vertex cover, okay, for example, if K is uh, constant, okay, so this, sorry, 2 to the K, okay, 2 to the K, sorry. So this is somewhat what the result we are going to see. But if K is something like constant, then running time is order V. If K is log n, log V, then the running time is order V into V, which is V square. Now if K is size of V, around size of V, then the running time is order V times 2 to the size of V, which is exponential. But see that these two are polynomial. Notice that these two are polynomial with respect to the input. So K, which is the size of the vertex cover that I am trying to find, if it is not too large, in other words, I'm not trying to find a vertex cover which is not too large, then the problem actually becomes easier. Okay. Now, now you might say, for example, what if I go? So, what is the trivial way to solve vertex covers? Trivial vertex cover algorithm. Okay. What is the trivial way to solve vertex cover? Well, I have a graph and I want to find the minimum number of vertices that will cover all the edges. So maybe that would be something like this guy covers 3 edges, no? And this guy covers 4 edges, okay, and so, and then I'll choose this guy which will cover these 2 edges, and finally I'll choose this guy to cover this edge. So all the edges are covered. So I'll say that there is a vertex cover with size at most. How many vertices have I chosen? 4. No. So this is an example. Okay. But how do I do it? What is the most trivial algorithm to do it? What is the simplest algorithm? I don't care about the running time. Let's say. Yeah. What is the simplest algorithm? I mean, the
Simplest algorithm for what?
To solve vertex cover. That is, check whether there is a vertex cover with size at most k.
Oh, I see. So then I would be taking, so I will start with the vertex, even though this is not necessary, but I will start with the vertex is about the highest degree. And then I'll see that, okay, if I include that vertex, then which all edges are going to be covered.
So you're trying to do some greedy strategy. I'm saying not even that. What is the simplest way? I mean, just let's say, what would be the lamest way to do it?
Okay, so anyway, then I will include a vertex and which is connected to the most number of many vertices. Okay. So then, if there is just to verify that whether is there exists a vertex cover of the size less than or equal or not. So then I will ask for the what I mean. Okay. So then I will ask for the assignment of which all vertices are the part of the vertex cover, and then I will check that whether all the edges are going to be covered or not.
Mm-hmm. Yeah. In other words, what you'll do is brute force, right?
Yes, sort of.
Okay, good. Yeah. So, well, what is the brute force approach? Well, approach. Okay, go across all vertices, vertex sets of size most k. Okay. So, but let's say I'm making the problem weaker. I just want to check whether there is a vertex cover of size exactly k. Okay, I'm making the problem weaker. Then how many sets are there? Well, from n, I'm choosing k points, so n choose k. So the running time is n choose k, order n choose k times something. Okay, let's say you need to go across all edges, so something like order n choose k times size of e or something like that. But what is more important is this guy. Okay, n choose k. Now, if k is constant, then it's not much of a problem. N choose k times e is something like n to the k, order n to the k times e. Right? Because if you, it will be something like n factorial divided by n minus k factorial, so on. So it's something like this. You multiply n k many times. Okay. This is polynomial. But if k is log, the number of vertices, it will be n choose k times e equals order n to the log v times e, where v is the number of vertices. No? So I mean n is the number of vertices. So this can as well, I can write it as n to the log n times e. Now this guy is not exponential. This is also what is called a quasi polynomial. Okay, n to the log n. This is not I didn't mean exponential. Sorry, this is not polynomial. So if you apply the brute force approach to solve vertex cover, in fact, this is a weaker problem. No, we reduce it to we modify the problem to be a weaker problem. Even in this weaker problem, when I talk about exactly equal to k, even in this weaker problem, the brute force is not able to achieve polynomial when k equals log n. Whereas the whereas this FPT algorithm, which I've not described yet how to do it, okay, is achieving polynomial when I increase k to log v. I mean, when I set k to log n. This guy is giving polynomial, this guy is not giving polynomial. So this is still an FPT algorithm. Don't be fooled. This is still an FPT algorithm where k is constant. Okay, which is actually a very bad case. But this is an FPT algorithm where k can be log n. Okay, and it can still give me polynomial time. So this is a better FPT algorithm. Although I've not yet described what the FPT algorithm is. Okay, I'll describe what the FPT algorithm is. Just I'm trying to demonstrate that what is the use of FPT algorithm, why, and you can clearly see that it does better than brute force. Okay, so now that I've talked about that, okay, we are going to talk about what the actual algorithm is. Okay, so we are going to concentrate on two types of techniques. Okay, parameterized algorithm techniques. Okay, one is called kernalization. The other is called branch and bound. Okay, kernalization. The other is called branch and bound. Now, what is kernalization? Okay, kernalization. What is kernalization? Reduce the problem into smaller subproblems that are easy to solve. Okay, and solve these smaller problems. Solve these smaller problems. So this might sound something like divide and conquer to you. Okay, but then what you do is you solve these smaller problems, and finally you get a hard unsolved problem because you solved all the other problems. Okay, you solved a hard problem. Okay, and but the size of hard problem is not large. Solve it, and this hard problem which is not large is what is called the kernel of the problem, kernel of the instance. Okay, this type of technique is called kernalization. In other words, like diagrammatically, if I want to represent something like this, you have this instance which is like a graph, let's say. Okay, and what you do is you start solving them. For example, vertex cover, you choose whether to add something in the vertex cover or not, and so on. You keep choosing, and then you have a much smaller part where the problem is actually very difficult. The others are solved easily. The problem is actually difficult in this hard part, but it so happens, okay, that this hard part, the size is very small, and even though I do apply brute force, the size of the kernel is so small that if I apply brute force, it is still running in polynomial time. Very small size, and this is what is called kernel. Apply brute force and solve. Again, to repeat, I break it into several. I break it into several fragments and then solve the easy instances, because the easy instances are numerous and they are easy. I can run. I can do it in polynomial time, and there is a part remaining which is hard actually, but it is so small that even if I apply brute force, which actually takes exponential time, it will take exponential time on the size of the kernel, which is actually very small, say log n. And since the kernel itself was very small, I solve it in polynomial time. Okay, yeah, Kishore.
See, when you say we fragment the problem, into smaller chunks.
Yeah.
So is it something randomly we do it, or do we have any such calculation based on that we fragment the problem?
Oh, okay. That is a good question. So by fragment, it is slightly unlike divide and conquer. Okay, I am not doing this parallelly. I am first dealing with a part, a small part. I solve this problem, then I have a remaining problem. Then I solve another problem, and then I have a remaining problem. I'll explain it in a while with an example. Okay, then I solve a problem. But so far, it is not happening randomly. Okay, usually it is a recursive process. Okay, I get smaller and smaller instances each time. Okay, and
But one more question, what it arises is, of course, we do it in a recursive way.
yeah.
But how can we segregate specific to kernel problem? So is it something kernel problem is spread across all the small problems, or it is concentrated on one of the section of the problem?
Yeah, exactly. So you need so you need some kind of theoretical guarantee that says that if these tests are not um, reached, then the size of the kernel is small. You need some kind of theoretical guarantee. Okay, which we'll see an example. You need a theoretical guarantee that says that if I can't do these easy operations, okay, and check that, you'll of course check that, and if it is not possible, then you'll come to the conclusion that the kernel is small. Whatever I'm left, first of all, whatever I'm left with is a kernel, and that kernel is actually very small in size. So there should be some kind of proof that will guarantee that. Okay, thank you. Yeah, good question. Now, so what we'll do is we'll look at the kernelization of vertex cover. Okay, now, so what is the kernelization of vertex cover? Okay, I'll just do the I'll just write the algorithm quickly, entire algorithm quickly, and then I'll talk about it. Okay, so what we are going to do is, so kernelization of vertex cover. Okay, I have an algorithm. Let me call it kernel VC. Okay, kernel VC, and the input is a graph G and K, a parameter K. So what is K? I want to check whether there is a vertex cover of size at most K or not. Okay. Now here's the algorithm. Step one is, okay, if G contains an isolated vertex V, delete V from G, okay, and delete V from G, and then what do? You do a recursion, okay. Return, you do a recursion. Kernel VC G, the new graph, which is G minus V, where V is deleted, and you set K as K. I'll explain these terms. Okay, I'll explain the steps in a while. Okay, second thing is, if G, if G has a vertex of degree at least K plus 1, then delete V from G, okay, from G, and then again I do a recursive process and say kernel VC G minus V, and this time I reduce K minus 1. Okay, now what I do is, now what I do is, now suppose step 1 and 2 are not possible anymore. Okay, and the size of the graph, okay, is large. Size of the graph, the number of okay, or rather I'll write the number of edges in the graph is more than k square, then output no. Okay, then output no. Or okay, I won't write this now anymore. Then there are two cases. Okay, suppose step 1 and step 2 are not possible anymore. Then there are two cases. If number of edges in that graph that we obtain, okay, at the end is greater than k square, then I can guarantee that there is no vertex cover of that much size. And whereas else, what I'll do is do brute force on G, which is not of a large size, and check. So where is the kernalization process happening? This is the kernalization process, or even this can be thought of as a kernalization process. Kernel, and this is the part which is not the kernel, which is solving that easy instances thing. This is called the pre-processing. Okay, now I'll explain what each of these terms mean. Okay, so what is the first thing that it says? If G contains an isolated vertex V, delete V from G. Okay, now step 1, what does step 1 mean? Okay, step 1 says what? If there is an isolated vertex, delete it. Okay, let's say I have a graph and there is an isolated vertex here. Okay, 1 2 3 4 5 6 5 and 6 are isolated vertices. Observe that 5 6 cannot be in the minimum vertex cover, because 5 and 6 are not covering any edges at all. So if it is not covering any edges at all, what is the use of including 5 and 6 in my vertex cover, right? So this is the first step of pre-processing, is I'll just delete 5 and the size of the minimum vertex cover remains the same. I hope you all can see that. For example, the minimum vertex cover here would be something like picking 2 and picking 4. Picking 4, I'll get these 3, and picking 2, I'll get these 3, and all edges are covered. 5 and 6 need not be included. I hope every one of you can see that. So I'll simply delete them. The size of the vertex cover remains the same. That's why I'll run the remaining algorithm on the G minus the isolated vertex, comma key will stay as it is. Now I'm still looking for a vertex cover which is at most. Is that clear?
Does K represent the minimum vertex cover?
So K represents the size of the vertex cover that we are looking for. We are looking for a vertex cover of size at most K. So in a way you can say that we are trying to find the minimum vertex cover. Okay, because if you find the minimum vertex cover, you can easily check whether it is at most K or not, and say that any vertex cover, if that is not true, then any vertex cover is greater than K. If the minimum vertex cover itself is greater than K. Yeah.
As part of step 1 pre-processing, the input given is G minus V, comma K. So G is a graph with n number of vertices, V number of vertices, Is that
So,
the
so
representation?
V here is an isolated vertex. Okay.
Oh, okay.
This small v, not capital V.
And K?
K is that initial K that is given, but K will change as you recurse. Okay. Because see, you can see that recursively I'm sometimes decrementing K also. Sometimes I'm recursively deleting, decrementing K also. So K may change.
Before step one,
Huh.
what we can have the K values?
What we can have as K values before step
Before
1.
step one.
So K, I mean, K could. So just looking at the algorithm, okay, K could be as large as polynomial.
As long as, okay.
Okay, K could be as large as n, let's say, the number of vertices. Okay,
Yeah, then,
yeah.
then let us suppose in step one we have deleted the isolated one. So that time the K value decreases, right? What it returns is decreased value.
So it returns the kernel VC of this. So I'm actually recursively calling kernel VC again. So what I'm saying is apply that algorithm on that smaller graph with the vertex V removed.
Yeah, in the first iteration, right? So let us suppose K with a graph 6 vertices and K also represents the 6 vertices. Then let us suppose 2 vertices are isolated. So in the first iteration, the output would be with the value K as 4, right? Out of 6 minus 2, it should be 4 for the first iteration.
Yeah, that's right.
Oh, okay.
Oh, okay. Wait. You mean if there are 2 isolated vertices?
Right.
No.
Out of 6 vertices?
No. If there are 6 vertices and there are 2 isolated vertices, the size of the graph becomes 4. K remains whatever it was. If you meant the size of the graph, then the size of the graph is reduced to 4 because you've deleted 2 isolated vertices. But K remains K.
I didn't get this key. What exactly it representing?
So K is representing the size of the vertex cover you are looking for.
Okay, size of the vertex cover. So it will be revealed. So but see what the return when it is outputting, it should give some value, right? Here for the K.
Yeah, but see, it's returning this subroutine. No, so this subroutine will again be run, and then that running process will go on, and then that may recurs again. And
in that stage, whatever the value it feels feasible, that value will be put into X, right? So let us suppose in recursive process of 10 iterations, after completing first iteration, whatever it feels the feasible solution, that value will be there.
That's right. Right.
It goes on changing as the iteration goes on.
That's right. Okay. But there is a logic. Okay, so there is a logic to why I'm not changing K. Okay, what is the logic? That if there are isolated vertices, they are not anyway covering any edges. Okay, so the size of my minimum vertex cover will remain the same. By including 5 and 6, I'm only going to increase the size of my vertex cover. Okay, so even if I delete this, that particular key remains the same. You get it, no?
Not exactly, but
okay, I'll give you an example. Okay.
Right.
So I'll give you an example. Let's say this is the graph G. Okay, and let's say K is the size of the vertex cover. So let's say K is 3, which means I need to look for a VC. Check if there exists a VC vertex cover with size at most 3. Okay. Okay, so this is what it means. No, since K is 3. Now I saw that if I pick this vertex 2 and if I pick this vertex 4, all the edges are covered. So this is a vertex cover. 2, 4 is a vertex cover, right?
Yeah.
Of size, what is the size of the vertex cover? 2, because I picked 2 vertices.
Yeah. That's the minimum vertex cover.
That is the minimum vertex cover. Let's see, even if it was not minimum, okay, because anyway I want to find a vertex cover if the size is at most 3. Even if I include 2, 5, if I include 5 to it, 2, 4, 5, 5 is an isolated vertex, okay, it is not contributing anything.
Right.
So even if I remove 5 from here, okay, I should, to explain it, I should have gone the opposite way. Consider this, okay, 2 for 5. Since 5 is an isolated vertex, if I remove it from here, I still get a vertex cover which is of size at most 3. No. You get it?
But when we consider 2, 4, 5, it's not a vertex cover, right? Is it?
It is still a vertex cover. It is still a vertex cover. It's not the minimum. Okay, I should not have talked about minimum vertex cover. It just started confusing you. Okay, I'll give you an example. Let's say a 2, 4, 5, 6. Okay, and this has size what? 4. It is not of size at most 3. But one thing you may observe is that if I delete 5 and 6, it still becomes a vertex cover, because 5 and 6 were not covering any edges only.
Yeah.
Right. So deleting isolated vertices will not change the size of the. It will not affect it. I should not. I don't know how to say it without saying minimum vertex cover, but let me call it feasible vertex cover. Okay, rather than minimum. Feasible meaning that it is less than the k parameter that I'm given. That is not going to change.
Okay. So for this example, right? When we start step 1, iteration 1, the KVL starts with 2, 4, 5, 6, and then the next iteration it comes to 2, 4, 5, and then next iteration comes to 2, 4. You get that? That's the way it executes.
Huh. So yeah, almost, but the actual way it happens in is, so if I have 1, 2, 3, 4, and 5, 6. Okay, if I have 1, 2, 3, 4, 5, 6, and this is my graph G. First, the step 1 is that remove isolated vertices. Okay, so I'll remove, let's say, 5 from here. Now what I'll do is I'll run the kernalization algorithm again on the remaining graph. Okay. Okay, I'll run the this on the remaining graph. Okay, and then what I'll do is, once I'll run step 1 again, which means I'll delete 6 from here, and then run the kernalization algorithm on the remaining graph. Okay, it gets smaller and smaller. Okay, just give me 2 minutes. Okay, I'll be back.
Sure.
Okay, just give me 2 minutes. वैसे हाँ मतलब आई थी नहीं Hi, yeah, sorry. Okay, so where were we? Okay, yeah. So we were talking about kernelization. No? So okay. So you see that deleting isolated vertices is not a problem. Now, next thing is what we are saying is if G has a vertex of degree at least k plus one. Okay, if G has a vertex of degree at least k plus one, then delete V. That is the next thing about kernelization. Let's say I'm not able to find any isolated vertices. What I'll do is I'm going to delete if it has a vertex of degree at least k plus one, then I'm going to delete it. Okay, one moment. So what I'm going to do is if G has a vertex of degree at least k plus 1, then I'm going to delete it. And not only am I going to delete it, I'm going to reduce this parameter k minus 1. In other words, what I'm saying is I need to pick that vertex. Okay. So what I mean is, let's say I have this graph. Okay, I had this 1, 2, 3, 4, 5, 6. Oh, sorry, what? How? Why do I have so many? Okay, it should not be 4. 1, 2, 3, 4, 5, 6. This was in the beginning. Now what I'm saying is I'm deleting these two. Now, uh, now I want to let's say k is 5. Suppose sorry, not k is 5, k is 3. Then every vertex which has a degree more than k. Okay, so let's say k is 2, not 3. It should be contained in a vertex cover of size at most 3. In other words, so I'm going to write it. Okay, if G contains a vertex V of degree more than k, okay, more than k, then V should be contained in every vertex cover of size at most k. Now, why is this true? Okay, why is this true? Because let's say you have a vertex and it has several, and this is neighbors, and this is like k plus 1. Okay, and I'm trying to look for a vertex cover of size at most k. Suppose I do not pick v, okay, for the sake of contradiction. Okay, I'm saying that what this says is, if this such a case happens, then I need to pick v. Otherwise, my vertex cover will not be of size at most. Let's verify that. Suppose I don't pick v. Okay, and let me call this u1, this u2, and u3, u4, and so on till uk plus 1. Suppose this vertex v is not picked. Then what happens? Unless I pick u1, this edge is not covered. Unless I pick u2, this edge is not covered, and so on. No. Suppose I don't pick v is not picked, then vu1, vu2, vu3, and so on till vuk plus 1 edges are not covered. So any vertex cover, since all the edges should be covered in a vertex cover, should contain u1, u2, u3, and so on till uk plus 1. It should contain it, because if it does not contain, because anyway v is not contained in that vertex cover. That's what we are assuming. No. Anyway, v is not picked. And now if I don't pick, let's say u1, then this edge will never be covered by the vertex cover. So it should be that u1 is picked, u2 is picked, u3 is picked, and so on. All these neighbors are picked if v is not picked, in order to cover those edges. Yeah, Kishore?
So it's again, I am reiterating the same question. So can we think k as an hyperparameter?
Can you think of k as a
Hyperparameter.
hyperparameter?
Right.
What is a hyper? What do you mean by hyper?
I mean, like, see, when we executing some algorithms, we fix the value. I mean, as in, we fix some value for that. Like, suppose the graph might give multiple vertex covers based on the k value. Like, suppose k is equal to 4, it gives 2 vertex covers. K is equal to 3, it may give 1 vertex cover.
Okay.
So is that something k should be what do we say, fixed by the by us?
Yeah, so I'll come to that. K is actually the parameter here. Actually, we've not discussed about the running time yet, but k is the parameter. That's right. Okay. But this is clear, right? Why? This is clear so far, right? If v is not included, then all of its neighbors should be included to cover each of those edges. Okay, right? Okay. Yeah. But what do you have if the vertex covers? Okay, so any vertex cover S, okay, any VC S should contain U1 and so on. But then what will happen? The size of the vertex cover, since it has U1 to UK plus 1, it's greater than K plus 1. Greater than equal to K plus 1. But what is the question asking? It is asking for a vertex, whether there exists a vertex cover of size less than K. No. So which is which means that if V is not picked, then I cannot get a vertex cover of size less than K. So any vertex which therefore any vertex cover of size K should contain V. if the degree of V is greater than K or greater than equal to K plus 1. So what does that mean? So we've come to the conclusion that, let's say, K is equal to 2. Okay. What is the degree of 1? It's 2. What is the degree of 3? It is 2. But what is the degree of 2? Degree of 2 equals 3. Okay. It's badly written. Degree of 2 equals 3. No, which is greater than K, because K is 2. So I need to pick 2. This is an observation that I make. And if the degree here also 4, K is greater than 2. So I need to pick, here degree is 3, which is greater than 2. I need to pick 4. Because any vertex cover with size less than or equal to K must contain these vertices. That is the conclusion that we make. Okay. And so what did we do? We have this graph, and what do we do? If it has isolated vertices, then remove it. If it has a large degree vertex, remove it, and so on. I keep doing this process. This is what is called pre-processing. Then what do I get? Then I get a case, which is my step 3 here. Suppose step 1 and step 2 are not possible anymore. Okay. I reach a case when I don't have any isolated vertices. I don't have any degree greater than K vertices. Okay. Then what do you have? Then, okay. Suppose no isolated vertices, and no degree greater than K vertices, then either the remaining graph, okay, the remaining graph G. Okay, by the way, why is this K minus 1? Where is this? Why is this K minus 1? What is the logic behind it? Since that V needed to be picked, I have, since this K minus 1 represents that now I need to look for a vertex cover of size 1 reduced, because V is already picked. This represents that one vertex is picked. Okay. And now from the remaining graph, I want to find a vertex cover of size 1 less, so that when I combine it with this V, I'll get exactly K size vertex cover. Is that clear? Okay. For example, in this graph, K is 2, so I need to find a vertex cover of size 2. I delete this, K is still 2 according to my step 1, and I have this graph out of which by the step 2, I delete this. Now what do I do? According to step 2, okay, I have found one vertex which is definitely in the vertex cover. So what do I do? From the remaining graph, I find a vertex cover of size 1 less, so that when I combine the vertex cover of this with this particular vertex, I get exactly K as the total size of the vertex cover. Okay. And so that is exactly what happens here. So suppose no isolated vertices are remaining and no degree greater than K many vertices are remaining, then either the remaining graph G, okay, has number of edges less than or equal to K square, okay, or it does not have a vertex cover of size less than equal to k. So what is this is my lemma. Okay, and because in interest of time I will not be going to cover why exactly. It's a bit of analysis, but take my word for it. Either there are either the first case is either the size of the remaining graph is small, the number of edges is very small, or it does not have a vertex cover of size. So what does it mean? If the number of edges is larger than k square, I can just count it. No, then I'll just say no. My output is no. But now, what is this case? Remaining g. Okay. So let's talk about case 1. Okay, that is this part. And I should have named it case 2, but leave it. So case 1 should actually be, so number of edges is greater than k square. Okay, then the first case, this then, okay, how do I okay. If this is greater than k square, then this cannot be applicable, so it must be that this is true. It does not have a vertex cover of size at most k. Then output no. Okay, case 2 is the number of edges is at most k square. Yeah, Kishore.
Yeah, see, with respect to case 1, edges greater than k square will be said. Is it when we consider undirected graph or directed graph?
So far we are only talking about undirected. Okay. And by the way, this I'm not talking about the graph that we started with here. Okay, I'm talking about as the changes we are making on the graph by deleting vertices and so on. Finally, what we obtain is a graph which has no isolated vertices and has no large degree vertices. Okay, because we deleted all of them. Okay, that is the graph we are talking about. Okay, and
so why I have asked this question is, see, in case of undirected graph, of course, because it certainly multiplies, because A to B and B to A, it counts for 2. But whereas directed graph, it won't be that way.
That's right.
So this condition won't exactly apply for when the graph is directed, right?
If the graph is directed,
E greater than equal.
First of all, if the graph is directed, how do you define the vertex cover? Are you fine with see, because
even that's another question I also have. So when it is directed also, we need to first how we'll define the vertex cover.
Right, exactly. Because to cover an edge, it is enough to pick any one of the vertices. That is a question that you want to determine. Because if is it, should I pick the one where the
I think even in directed graph, anyway, the isolated areas are always isolated.
Yeah.
Irrespective of directed or directed. The second case is degree. So degree also will be same. See, let us suppose when we pick one
the degree, you should be considering the sum of the in degree and out degree. If you only considering out degree, then
but in undirected, right, we are considering what I understand is, probably I might be wrong, what I understand is outgoing degree.
No, but in an undirected graph, outgoing degree does not, nothing is going out or in. I mean, or equivalently, everything is going out and everything is also going in.
Right. So, but there we are counting when we say degree in undirected graph for this problem or algorithm, we are counting in terms of outgoing, right?
No, not necessarily. Not necessarily. I mean, for example, let's say you have this, then you would say, according to what you said, no, see, first of all, it really depends on how you define vertex cover in a directed graph. Okay. So, let's say in a directed graph, how do you define the vertex cover? to cover an edge, okay, let's say I want to cover this edge. How do I cover it? Is it enough to cover any one of the two vertices? Or should I be covering a vertex from which the arrow is starting? Or should I? So that is one thing you need to fix at first. So if you say any one of the edges, if any one of the vertices on either side of the one more good, if any of the vertices on either sides of the edge is allowed to be covered, is enough to cover the edge according to your definition of vertex cover in directed graphs, then it is very similar to this. The algorithm would be very similar, except you will also be counting the in degrees. Here, go ahead.
So then I mean to say that the vertex cover for the directed graph could be like, say, representing the directed graph as a combination of the strongly connected components. I mean, that's what I'm saying. So,
you could do that. What I mean to say is that there is no correct way to define vertex cover in directed graphs. Okay, there is no correct way. I'm saying it depends on how you. I'm not saying one way to define it is wrong or right. If you say just consider one vertex, either one of the vertex to cover an edge, that too is fine. You may have a different algorithm for that. And if you consider vertex cover to consist of both the not both the vertices from which the arrow is starting or where the arrow is ending, either ways, maybe the definition, the algorithm may be different for that. Yeah, go ahead, continue. You were raising your hand.
No, it was a mistake.
Oh, okay, it was by mistake. But yeah, sure.
Yeah, see, of course, see, that's what. See, when we take individual directed and indirect graphs, of course, as per the graph definition of undirected and directed graph, we consider that. That I understand totally. But when we are trying to solve this parameterized, type of algorithms, okay, and that too in case of this pre-processing, and then the next step what we have is after pre-processing, what we do, I just forgot that name. See, when we are doing these steps, right? Do we have a different way of resolving the indirect graph and then directed graphs, or the same?
That's what I'm saying. How do you define vertex cover in directed graphs? You can choose your definition. Tell me your definition of vertex cover in directed graphs.
So basically, what my understanding is, the outgoing arrows, of course, the same edge will considered as in degree and out degree as well, in undirected graph.
Okay. So what you mean is this? Okay, so 1, 2, 3, 4, 5. Then the direction does not matter. That's what you mean, no? To cover an edge, I can either choose 1 or 5.
Yeah. See, if let us suppose in undirected graph, if the vertex is attached with 3 edges, I think the degree is 3 for that with respect to that vertex.
Okay, what do you mean is regardless of outgoing incoming? So what do you mean is the sum of outgoing incoming?
And same for the directed graph. Let us suppose vertex X having 2 incoming edges and 2 outgoing edges.
Okay.
What I think is basically with the respect to outgoing. So in that case, what I say is 2 is the degree for that vertex, and when we specifically say that out degree and then in degree, then I will mention as per that.
No. So that's what I'm saying. If that was your definition of vertex cover in directed graphs, then the degree that you are considering should be sum of the in degree and out degree, and the same algorithm will still hold.
Okay.
Because if you are saying that if the graph is directed to cover an edge, I can either choose to cover this edge 1, 5. I can either choose 1 to be in my set or 5 to be in my set. Okay, anything is fine regardless of this direction of the arrow. Then I may as well just convert it into a undirected graph. No, any vertex cover will still be a vertex cover.
Even in undirected graph, we are not considering either the direction of the arrow. It's just we are taking the number of edges.
Exactly.
So same way, Okay.
Exactly, because this is how you define vertex cover in directed graphs. Now, if you say that okay, I can only choose vertices from which the arrow starts, then you may. Now this conversion is not anymore true. Maybe there's a different way to do it. Okay, that's what I meant by it depends on how you define vertex cover in directed graphs. Okay.
Okay, but basically, this problem will be solved as per what we defined, right?
Exactly.
As
Exactly. Exactly. There is no one correct way to define it. Okay.
Okay.
Okay. Great. So now what we have is we have the case one. Okay. After deleting all those isolated vertices, this and that, so on, the pre-processing. Either the number of edges is greater than k square, in which case I'm saying okay. There is a simple analysis for this. You can check out the lectures. Okay. But in which case we are saying that if this is not true, that is number of edges greater than k square, then it definitely does not have a vertex cover of size at most k. So then even going further anyway would not make sense. So we'll just output no, it does not have a vertex cover of size at most k. Okay. But if this number of edges is at most k square, what do you do? Any idea? Number of edges is at most k square.
That vertex should be picked.
Which vertex? Now we are just saying the number of edges in that remaining graph is at most k square. Which vertex should be picked?
Okay, this is the number of edges. Okay. So the vertices which are connected to these number of edges.
Oh, okay.
The leftover edges after pre-processing. So when we get the number of edges, whatever.
So if you have this graph and some are isolated vertices, you deleted them. Some are high degree vertices which have greater than equal to k plus 1 degree. I pick them. Okay. And I have this part remaining whose number of edges is at most k square. Okay. I have this.
So now what I should say might be the kernel.
Exactly. This is the kernel. Okay, this is the kernel. Right. And this is the kernel, and furthermore, the size of the kernel is small. It is at most k square. I've found an upper bound in the size of the kernel. Now what do? I simply brute force and check if there exists a vertex cover of size until that particular recursion step, whatever k value. I mean, k could have decremented, right? Because some places I'm doing k minus 1 and doing recursion, new value of k. So let's say it is k prime. Okay, vertex cover of size k prime is in the kernel or not. And how much time is it taking? N choose k prime. We already saw that why it is the case. And n choose k prime is something like n to the k prime. Right. Now if yeah, Kishore.
See, based on our discussion, what the k value is, we are deciding at the end of the brute force, right?
What this k value we are deciding
is end of the brute force.
No, see, first there is a k which is given as an input by the user. There is a graph and a k.
Okay.
Now what is happening is I'm recursively deleting some vertices. I'm deleting some vertices. I'm accordingly deciding whether to keep k the same or decrement k.
Okay.
And finally what happens is I'm getting to this kernel step where I cannot find any isolated vertices to delete. I cannot find any large degree vertices. By large degree I mean greater than k plus 1, greater than equal to k plus 1 degree. And I have this kernel left. Okay, and some value of k which I'm for the sake of so that you don't get confused, I'm calling it k prime, which is the value of k that has decremented until that kernel is obtained.
So is this, can we say, a statement k prime is always less than k?
Yeah, you can always say that. In fact, I'm going to use that. K prime is always. So what do you have? So k prime is there or not? So how many to when brute forcing, I'm deciding whether to include a particular vertex there or not. So if there are at most k square many vertices, because there are k square many edges, I can assume now there are no isolated vertices. I can even assume that there are at most k square many vertices. So to include that k square many, to include whether k square many, um, to include or not include one of the vertices, I'll take 2 to the k square, right? 2 to the k square, the 2 to the k square time, because 2 to the k square many different subsets of this remaining of the vertices of this remaining kernel will be there, right? It is nothing but the power set of the set of vertices. In other words, I'm finding all possible subsets and checking whether that is a vertex cover. So solving kernel takes 2 to the k square times, I want to check whether it is a vertex cover or not, which will be some order k square, let's say, which is linear in the number of the linear in the size of the kernel time. And so the previous thing, which we are going across the graph and checking whether isolated vertices are there or not, checking the degree and so on, will take something like order the number, the size of the adjacency matrix, which is, so total time equals order the pre-processing step, which is taking something like the number of vertices times the size of the adjacency matrix. Each time I'm either checking for I'm going through the adjacency matrix and checking whether there is an isolated vertex or not, or I'm going through and checking whether there is a vertex of degree k plus 1 or not, greater than k plus 1 or not, plus this kernelization time, which is 2k square times order k square. This is the total time. And therefore you have that if k is log n, then order, so it's something like order n cube plus 2 to the log n square, which is something like 2 log n, 2n, with something like 2 to the 2 log n. Okay, so this is a bit incorrect. So k square is a constant. K square needs to go through each of the k square, 2 to the k square time. I need a better bound than this. But anyway, k, I can replace it with some k prime. It's okay. I can replace it with some k prime. K prime. I'll just have a factor of, squaring factor or something like that. But it's okay. So 2 to the log n, I can take this as k prime times order k prime times log n. And you can see that this is polynomial. When my k is something like log n, order log n. Okay. So this is an example of parameterization. Okay. What I do is I keep dealing with the easy cases And after dealing with all the easy cases, I realized that there is one chunk which does not satisfy these easy cases. So it's a hard case, but it so happens that the size of this chunk is very small. For example, in this case, the size of the graph that I get remaining is small. And it so happens that it's so small that I can actually do brute force and then finish the job. Okay. So
is this the standard practice of solving or designing the parameterized algorithms for the problem?
yeah, exactly. This is a very standard algorithm. I mean, this is a very standard way to do things in parameterized complexity.
So
Okay.
can you summarize these three steps again that while solving a problem through the parameterized algorithm, what do we do? So what are the standard steps?
While solving.
While solving, while designing a parameterized algorithm for a problem, if it exists, then what are the standard steps?
Okay. So what are the standard steps? Okay. So what do you do in kernalization? This is only one way to build parameterized algorithm, by the way. Okay. In kernalization, you do pre-processing. Okay. In pre-processing, what do? You solve easier instances. You solve all easier instances. And when you solve all easier instances, what do? It gives rise to a kernel. Okay. It gives rise to a kernel. Now, this kernel, I can always have exponential size kernels, okay, which may be a problem because maybe I cannot parameterize it properly, but regardless, it's a kernelization. Okay. After pre-processing, I get this kernel. Then what do? Solve the kernel. So the kernel is the hard case. Now, if the kernel is itself exponentially sized, then there's not some much we can do. Okay. But for example, here too, the kernel was of exponential size with respect to k, but we can accordingly adjust k a bit and then get something. Okay, something that may work. Okay, and but if the kernel size is still small enough, then we can easily solve the kernel and do by doing brute force. Okay, so this is a summary of how kernelization works. Okay, now
yes.
Okay, now. So I'll just give you another quick example, but it's almost 8 o'clock. I was not able to do branch and bound, sadly. But tomorrow we have an extra session. Maybe I can do a bit of branch and bound tomorrow, and then do the rest of the extra session. Okay. I'll quickly finish this. This is what is called the edge click cover. Okay. So the edge click cover problem means given a graph G and a K, which is an integer or a natural number, let's say. Okay. Decide whether edges of G. Okay, again we are doing something like vertex cover only, but this time we are talking about click cover. Okay, edges of G can be covered by at most k clicks. Decide whether edges of G can be covered by at most k clicks. Okay, and let's say I have a let's say I have a graph like this. Okay, let's say I have a graph like this. So how many clicks are, no, what are clicks? They are complete, small complete graphs. So how many clicks are required to cover it? This is one click. This is a key for, right? This is another click. And This is another click. This is another click. This is another click. I don't have enough colors right now to represent them, and that are required to cover all the edges. Notice that isolated vertices again don't play a role. If I pick isolated vertices, it does not matter because they are not covering any edges. Okay, and this is the first observation. And okay, how? So what is the answer here? A the number of clicks to cover is 1, 2, 3, 4, 5. So 5 clicks will cover this. Anything greater than 5 will still cover this. Okay. Although isolated vertices are also clicks, they are not contributing anything. That is the first thing. So what I can do is I can delete the isolated vertices without having any problem. And then I have this remaining graph. Here too, you'll realize, okay, that what I can do is I can, if I have isolated edges like this, okay, then I need to pick this. There is no other way. Because if I have an isolated edge, what do I mean by isolated edge? It is a single edge floating around like these two. Okay, isolated edges, if I have this, I need to pick this because this itself is a click and no bigger click contains this. So I need to pick this. So what I'll do is I'll pick and remove from graph. So I'll delete this from graph, and since I had to pick this, I'll reduce k by k minus 1. New k is k minus 1. Then I'll do the same thing for this also. I'll reduce it by k minus 1. Okay. Now, finally, what I'll do is, finally, this step 1 is isolated vertices. Step 2 is isolated edges. Step 3 is, if it so happens, suppose for a UV, if U, now neighbor of U is equal to the neighbor set of V. So every neighbor in U is also a neighbor of V. Okay. Then what happens? Then any click containing U, any maximal click containing U should also contain V. Why? Because see, this is U, okay. U has some neighbors and U is connected to V and V also has the same neighbors. Okay. So if U is contained in a click, so U is contained in a this complete graph. So this is a complete graph. Then V is also connected to that complete graph. So I can form a bigger click by containing V. So I've reduced the total number of clicks in order to cover the entire graph. So if I either remove U or V, one of them is already representing the click that I should be picking. So I can safely remove one of the vertices. Okay, so delete one of the vertices, let's say V. Yeah, Kishore.
See, UV, that's fine. But when we remove V or U, so we are also removing, we are missing one more edge, right? So let's suppose when we consider both the clicks, U and V, okay, we got probably 10 edges altogether.
Yeah.
10 edges. So if we remove V, then we'll be missing with one edge, right? UV edge.
Yeah, exactly. Not only UV edge, we'll be missing all the edges which it was connected to each other's neighbors.
Right.
Yeah, right. But notice that if I delete V, the number of clicks needed to cover this graph is not decreased or increased. It remains the same. Notice that fact.
No, it will be decreased by 1, right?
Exactly, it will not be decreased, because if any click that U is a part of, V is also a part of that click. Together they form a bigger click. Always. So even if I delete V, okay, even if I delete V, even if I delete V, you will represent the click, the original click minus some of the edges removed, but it will definitely be inside that click. Okay, it requires some thought. Okay, it requires some thought.
So in that case, right? So this case will not be only with U or V. It might be apply. It might apply to other clicks also. Right? Let's suppose U V. We have other vertices like X, Y, Z. Even for the same, the other vertices also it applies same.
Yeah. So the algorithm will look for the other vertices also and check whether their neighbor sets are same. If the neighbor sets are same, then I'll delete one of them, and without losing the number of VC. Okay. So what I'll do is
this will be done as part of brute force, right? This removing the click.
It's brute force, but it's not a very bad brute force. I'm only going across all edges. I'm not going across all sets of size k or something. So even if I brute force, it's still polynomial because there are only polynomial many edges. Okay, so I'll remove that one of the vertices V and keep k as the same thing. Okay, and there is actually a proof. Okay, but that proof is actually not very difficult. I can do it tomorrow, but what we get is at the end, I'll do that proof tomorrow. Okay, the kernel size is at most 2 to the k. Okay, I'll do it tomorrow, and if it is at most 2 to the k, then I'll do the same business here. Now I'll go across each particular possible subset and then check into the k and the thread. Okay, and this proof I'll do tomorrow, and then my kernelization will be complete. Okay, so it's a similar idea here also. So this process is called kernelization. Anyway, I've taken more time than I imagined. Tomorrow we'll do a bit of this remaining proof. I also want to quickly discuss branch and bound, and then I'll do an entire recap of the course material. Okay. Okay. Any more questions?
Yeah.
Yeah.
And I believe tomorrow the same time, right?
Yeah. Tomorrow the same time, 6 p.m. Okay.
Thank you.
Okay. Thank you, Kishore. Goel, any questions?
No, thank you so much.
Oh, okay. We'll meet tomorrow then. Okay.
Sure.
Okay. Bye bye.